We are going to start by going over the worksheet from yesterday, the review worksheet. If anybody needs a copy of it, I've got it right here. Okay. And then after that, we're going to start talking about vectors. I do not anticipate that we will get far enough that you guys could start on the homework, and so I have not even posted that yet, because we're just going to start our discussion of vectors today. By tomorrow, you will have enough that you can get in and do, if not all of the homework, darn close to all of the homework. Okay? But I do want to start with going over that worksheet. I will be collecting the worksheet for completion credit, and I will work through anything that you guys got stuck on and need to see. Okay? So I'm going to start just by giving the answers, and if you need to see how I got that answer, I'm happy to, but if nobody speaks up, I'm just going to move on to the next problem. Yes, ma'am? Yes, I am going to collect them for completion credit after I go through and answer any questions that you have about them. Okay? So on number 1, the answer to number 1 was 6.215 feet. Yep.
I got 6.266. Does that count?
I would count that as close enough. Huh? 6.216, I would count. 6.19, I'd count that. What I'm not going to count is like 27 or like, it's got to be ballpark here. I use law of sines on this one. Let me draw a quick picture for how I saw this one. I've got yours right over here, dear. I'm going to do my best with my picture here. So I realize that this is a lot more than 12.3 degrees, but if I make my triangle more narrow, it's harder for me to write that in. So 12.3 degrees there, and it's 21 feet long, forming a right angle. And what does this represent here? The height of what? Not the height of the ramp. Of the building. It's like we need to get up this high because that's where the opening in the building is. That's where the door is. And it's just like straight brick wall or concrete or something up to that point. That is not going to change when they put this new ramp in. They're not rebuilding the structure. They're just putting in a new ramp. So when they go to put this new ramp in, the only way that they're going to be able to reduce that angle, since it still has to go up just as high as before, is going to be to pull it out like this. This is our new ramp. This is our new angle of 9.5 degrees. And we are wanting this distance right here, because it says how much farther. I don't need to know from the building to the end of the ramp. I just want to know how much farther than the old ramp. How much are they going to be pushing into the parking lot beyond what they were before? Does that make sense? So the way I went about doing this problem, I found this angle over here by doing 180 minus 12.3. And I got, 167.7. And then from here I used law of sines. This 9.5 degrees is across from this side over here. And so I could set up 21 feet over sine of 9.5 degrees is equal to, we're looking for x across from X is this angle up here. So I need that angle up there. How would I find that angle? How would I find the angle with the pink question mark on it? I do 180 minus 167.7 minus 9.5. Does anybody happen to have that value? .8. So I would have sine of 2.8 degrees. So that's how I set that particular problem up. They did not ask me for the new length of the length of the new ramp. They said, how much farther out from the dock will that put the foot of the ramp? So foot of the ramp, how much farther would be that right there. If it had just said how far, then I think the wording wouldn't have made it as clear that I was looking for that little piece down at the bottom. It's that how much farther, like we were already extending into the parking lot with this ramp, and then I had to extend it out even further. Does that make sense? Okay. Yeah. And I will do my absolute Boy Scouts honor best on the test on any story problems that it's very clear what thing I'm asking about. If you're not sure, like if I give you a ramp problem, you're like, based on the wording, are you looking like, come up and ask me, okay? What I want to be testing you on is, do you know how to apply law of sines and law of cosines to solve different triangles in real world situations? If you're struggling with like, you asked for this, but I still don't know what you mean, come and talk to me, okay? Number 2, you needed to find all 3 angles because they gave you all 3 sides. When they give you side, 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 you're going to use law of cosines every time. Side, side, side is always law of cosines. I don't know what you called your angles, so I'm going to use the building names for the School of Ed. That angle is approximately 36.87 degrees. The angle for the School of Fine Arts, that angle was approximately 53.13 degrees. And where everybody thought they'd made a mistake, the angle at the pharmacy was dead on 90 degrees. Exactly. Yes, ma'am. Then I would look at your rounding on the other things. But 90.001, if you put that down and it was supposed to be exactly 90, you are within 1/1000th of my answer. We're good. When I read this problem, before I even used law of cosines here, I knew one of those angles was going to come out to be 90. Does anybody see how I knew that just based on the story?
Right triangle one of the things.
Yeah, what are the lengths of the sides?
Pretty like 5.3.
Yeah, 0.3, 0.4, 0.5. That's a 3, 4, 5 triangle. 3, 4, 5 is one of our Pythagorean triples, so we know it has to make a right angle. Does that help? Anytime you see multiples, whether it is multiples created through multiplication getting bigger, or you multiply by a fraction or a decimal so it's actually smaller, you've got a 3, 4, 5, it's a right triangle. Number 3. We are looking for this distance right here. They told us that this was 42 degrees. That was 2.15 feet. Would this be law of sines or law of cosines? Hmm?
I use some because there's an isosceles triangle, so those.
Yes. You can use law of sines because it's a isosceles triangle, and so you can use that information to get your base angles. Using just what they gave you without finding the base angles, this would be law of cosines, but you're correct. You can use law of sines on this one. They gave you side angle side. If you're going to use law of cosines on this, then you would need angle side angle. Do you guys need to see how I set this one up using law of cosines, or are we okay? If you change your mind, speak up. Yes, ma'am.
You accept every like rule for like law of sines, law of cosine, like side,
Mm-hmm. Yes. For law of cosines, side, 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 and side angle side. For law of sines, angle, angle, side, angle, side, angle. You can do side, side angle with law of sines, but this is the one that's the ambiguous case. So we can use it there, but we have to be careful because we have to watch out. There might be more than one triangle that meets those conditions. Yep. Number 4. This was north 59.793 degrees east. You've got Chatham Tap right here. Alex leaves and heads straight south. Says he runs to his dorm room. So he goes 0.2 miles. Alex is meandering much slower up towards Hinkle Fieldhouse. He doesn't make it very far because he's not running. He's just like strolling along. And then we are also given that the distance between these two is 1/4 of a mile. So they've given us side, 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 which tells me I need to use what? Law of cosines. Side, side, side means law of cosines. And then carefully reading what they said. It said, at this point, what is Ben's bearing from Chatham Tap? So from the position of being right here, what bearing would you need to take to get to where Ben is? So I can see we're obviously going to need to head north. And we would need to head east, but it's this angle right here, outside of the triangle, that I would need. Well, if you look at that, my bearing angle, I have to use a north-south line. Alex ran straight south. So what that means is that to find that bearing angle, I can do 180 minus theta, and I'm going to call this right here theta. To get my bearing angle. Pedro, is your phone behaving itself? Can't even hear me, so I'm going to go with no. Yes, ma'am.
So, how do you know it's 180 versus 90?
Yep. If it's a line like this, that's 180 degrees. That would be 90. So if you're looking at like a northeast quadrant, that would be 90. But because we have part of our triangle is heading straight south, and we're going to need to head northeast, I can use this north-south line, which would be half a circle, 180 degrees. And then I can just subtract off that angle that we can find from our triangle to get the bearing. Okay? Do you guys have any other questions about number 3 or number 4? Yes, ma'am.
Just on your canvas. Like,
Will it be on Canvas? Yes, I will post the answers on Canvas. If you need to see more work than this, let me know.
Okay.
Because it's only the work that we're doing together that I'm going to post.
Can we take another one of these home?
Absolutely. Yes. Yes, yes. Number 5 was really similar to number 3. Number 3, you could choose to use either law of sines or law of cosines. With number 5, it's definitely a law of cosines problem. Because it's not an isosceles triangle, so I don't have enough information to find the other two angles. They've given us side angle side, so law of cosines. This one you should have gotten that distance was approximately 22.879 yards. Yes. You're finished? Thank you, sir. Do you guys need to see this one worked out further? Okay. Number 6. What information are they giving you to work with here on number 6? Sides. You have side, 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 which means what? Law of cosines. So we have Weidman is 7 feet away from Baldwin. Baldwin is 10 feet away from Martin. And then Martin and Weidman were only 4 feet from each other. I thought the hardest part of this problem was figuring out which angle they're asking you to find. It says, find the angle at which Martin is standing. So Martin is right here. This is that angle that you're looking for, the one across from the 7 feet. And that angle is about 33.123. Do you guys need to see that one out further? Okay. Number 7, I would not have used law of sines or law of cosines on this one. Number 7, it tells us that we've got a tree. And that tree is going to need to be staked down. And the rope that they are using to stake it is 17 feet long, and I just drew that on the wrong question. There we go. It says the angle of elevation is 62 degrees. Remember, angles of elevation start from a horizontal, and then they go up from there. Angles of depression, you start from a horizontal, and then you go down. But we always start from a horizontal with elevation or depression. They wanted to know the height of the tree. This is just sine. It's not law of sines, it's just sine. We want to know the opposite side. We have the hypotenuse and we have the angle. So sine of my angle is equal to opposite over hypotenuse. And I got that the tree was right about 15.01 feet. So far, so good? Number 8. What did they give us? They gave us our sides. Side, side, side means law of cosines. We had 200 yards. And that was the first part. Then 150 yards for the second leg. And 300 yards for the third leg. They want to find the angle created by the intersection of the first and last legs, so this right here. So I'm going to call that alpha. That angle was right about 26.384 degrees. You'll need that right there. There's an extra copy right there for you. The very last problem, I'm sure there's a fancy way that you could do this with law of sines or law of cosines. I looked at it, and I did it with inverse tangent. I didn't use law of sines or law of cosines on this one. We have Resco down here. The student walks due west for 0.2 of a mile, and then they turn and they go due north. So they're telling me right there that we've got a right triangle. If I have a right triangle, I can just use basic right triangle trig here. And they took that up to Robertson. We've been asked to find the bearing that they would need to travel to head back to Resco from there. Since we always do bearings on a north-south line, this is the angle that I'm looking for. And that's inside my triangle, so I don't have to get fancy with any kind of 180 and 90 and add and subtract. I just need the inside angle, and that will give me my bearing. So since I have opposite and hypotenuse, I have opposite and adjacent, I'm using tangent to find that. So I have tangent of the angle that I'm looking for is 0.2 over 0.23. To isolate that angle, I would use inverse tangent of 0.2 over 0.23. I know I'm going to have to head south. I know I'm going to have to head east because he originally traveled west and north, so reversing that process, and the angle that you should have come up with was about 41.01 degrees.
Is it calculated as 41.009?
Yes, 41.009 would be fine.
It's 40.976 word.
Yes. Yeah, I would take that. Because at that point, you are within literally just a couple thousandths of my answer. Yep. For anything that differs from my answers, I definitely, whether it's test or this worksheet or whatever, I want to see your process. Because if the difference is related to like you chose the wrong method to get there, that's a conversation we need to have. If it's due to rounding on the calculator, that's an entirely different conversation. And if it's due to rounding on the calculator, I'm not nearly as concerned about it as whether or not you're using the correct process to get there. Before you guys leave the room, please make sure you turn these into the basket so that I can give you your completion credit. It's going to go in as a homework score. Okay? If you're not all the way done with it yet, because we got it set up, but you had gone off track with it, just make sure you get it to me before the end of the day. Okay? I passed out a stapled sheet of paper. Those are our guided notes that we're going to use for vectors. So you guys don't have to write everything down. So I had my little meme up at the beginning. Vectors have both direction and magnitude. What is magnitude? What'd you say? Like force. Yes. Magnitude is describing the strength of that direction. Scalars have magnitude only. Vectors have magnitude and direction. Can you guys think of some examples of scalars for me? Things that only have magnitude. Speed. Mass. Energy. Temperature does count, yes. I hear some whispering and I thought I heard a scalar. What'd you say? Distance. We could keep going on with scalars. If it has a value associated with it, but not necessarily a direction that goes along with that, then that would be a scalar. This is a great opportunity to do some point counterpoint. So mass is a scalar. Weight is a vector. This is why weight and mass are related concepts, but they're not the same. Your mass, that's how much stuff makes you. Your weight is how much stuff makes you, the magnitude, but it also has a direction with it that's associated with gravity. That mass is being forced downward into the ground. That's what your weight is. So if you go to a different planet, your mass stays the same, but the force pushing you down onto the ground changes. Does that make sense? So related, but not the same. I know in science class they used to hound all the time that mass and weight were different, mass and weight were different, and then they would almost use them interchangeably. This is the big difference here. Point counterpoint with distance. Distance is a scalar. Once you include a direction with that, then it's displacement. Displacement tells me distance and direction. Can you guys think of any other things that have both magnitude, force, and direction? Velocity. Acceleration. Have you guys ever seen maps of electric or magnetic fields? Usually they are vector maps. I'll see if I can find one. I would attempt to draw one, but no. But a lot of times when you look around like the North Pole and they're showing the magnetic field, it has all these different arrows of different lengths that are like making this swirl pattern. That is a vector map. So electric fields, magnetic fields. And just like the other, we could keep going on and on and on. I'll see if I can find a good example of a vector map. One of the things that I always think of when I'm thinking about vectors is the forecast. When they're talking about the wind is going to come from this direction, and if it's just like a cool breeze, we would represent that with a short arrow. It doesn't have much force behind it, but it's blowing in this direction. If it's blowing much harder, I would represent that with a longer line, but it's still going the same way. So from a graphic perspective, vectors that have the same direction and magnitude are equivalent. Location doesn't matter. Direction and magnitude are all that matter. Location is irrelevant. Because the location doesn't matter, when we're looking at an XY plane, we can move vectors around. Think about the wind. If you stand outside next to me and I feel wind on me, is there any chance that, like, if it's blowing really hard, that you don't feel it? So the location doesn't really matter here. It has the same direction and the same force behind it. Vectors can be moved. As long as neither the magnitude or the direction are changed. Direction and magnitude need to be preserved. If the initial point is on the origin, then we say that it is in standard position. So if I were to draw a vector, the initial point is here. This vector right here, I'm going to call this vector u, is in standard position. Any other vector that has the same direction and the same length is equal. So if I were to draw another one right, I don't know, I could put it here. If I call this vector v, vectors u and v are equal. I could have one over here. call this one vector A. Same direction, same magnitude. So if you think about it like rise over run, if it's the exact same length and you did the same slope to get there, these vectors are equal. This is my initial point. We put an arrow on the terminal point. We can do something called vector addition. If I have a vector, I'm going to call this one vector B. Because location doesn't matter, I can add two vectors together by putting them tip to tail. So here's my vector B. If I have a vector C here, where I've placed them tip to tail, adding those two together means that I go from the tail of vector B to the tip of vector C. And that would be vector B plus C. It doesn't matter whether I put C on the tip of B or whether I do it the other way around. They're going to end up with that same final position. Almost at a stopping point for today. We will still be dealing with bearings as we talk about vectors, because we want to talk about the direction of the vector. And often we will discuss that in terms of rotation. You could be given a quadrant bearing like what we've been doing, north 32 degrees west. But then there's also something called true bearings or headings. We still go from a north-south line, except we always start from north. If I was going to talk about a heading that went straight south, I would say that that was a heading of 180 degrees. Because I start with north as being 0, and then we would travel clockwise that many degrees. Does that make sense? So if I wanted to head west, my heading would be 270 degrees, because that would take me 3/4 of the way around the circle. I don't want to get too deep into that right now. We'll talk about those when we get to story problems. This is where I want to stop, and we'll actually find the component form tomorrow. Component form for a vector translates the vector into standard position. So we will find the change in x by doing x2 minus x1. We will find the change in y by doing y2 minus y1. Very last thing that I'm going to mention is this notation right here. This is called wedge notation. When you see wedge notation, it's referring to a vector. It's so that we don't get it confused with ordered pairs. We don't get it confused with open intervals. When I see that wedge notation, I know immediately that we're talking about a vector and that that vector is in standard position. So tomorrow we'll start off by finding component form for these two vectors, and then we will practice with finding magnitude and direction. All right?